talking about AGN feedback, and if I were giving this talk several years ago, that would have been probably a purely theoretical concept without too much observational data. But this is an area of observational astronomy where there's been a huge explosion in the data availability and in the methods that we use, and so there's no way that I can do justice to this topic. So instead I will just provide a brief, small sampling of various methods that we use now to look for AGN feedback. I will start with talking about the mechanisms that we're thinking about when we talk about AGN feedback, and then just march through some observational techniques that we've been using recently, observations of ionized gas, some really interesting, very recent work on finding extreme ionized gas outflows at high redshifts, something completely different using Sunyaev-Zildovich effect, and then Rachel Alexander will spend a few minutes talking about her recent paper on quasar winds and radio emission. All right, so what do we have in mind in terms of the mechanism of AGN feedback? So on small scales, we usually talk about two different processes. One possibility is radiation pressure-driven winds, or something you may have heard of, line-driven winds. This is a numerical simulation of this process with the accretion disk here along this axis, and the UV photons produced by the accretion disk get absorbed here in the sweet spot of high opacity, and that produces these quasi-equatorial outflows, which are extremely fast, a good fraction of the speed of light, but this is on very small scales, so this is 1,000 Schwarzschild radii. Jets can also produce strong outflows, and jets are very fast and strongly collimated, but if they propagate in extremely gas-rich medium, they do slam into this medium, form these bow shocks, and fill up this cocoon of hot gas. So now this is a very overpressured bubble that is now expanding because it is very strongly overpressured. And so it is much more isotropic than you would expect just from the fact that the jet itself is very strongly collimated. So a very important point that I would like to make here is that if we're looking for AGN winds on large scales, the scales of the host galaxy, then the morphology of the stuff that we see on large scales critically depends on the ISM structure in the galaxy, the distribution of the density in the interstellar medium of the galaxy, not on the input morphology. This is a numerical simulation by Alex Wagner of a disk galaxy, which is perpendicular to the screen, and the red stuff is the high-density clouds. And when they launch an outflow, what happens is that the outflow looks for the paths of least resistance. And so it carves these low-density channels in between the high-density clouds, and then once it reaches the scale height of the galaxy, it breaks out and produces these big bubbles. And of course, these big bubbles are well known from observations of starburst galaxies. It's the same physics. But the key point is that the morphology of this is dependent on the morphology of the galaxy, and we see the exact same result even if they launch jets in this galaxy every which way. Theoretical models of AGN feedback predict that if this is a relatively isotropic distribution of gas, then you expect to see outflows driven by quasars of about 1,000 kilometers a second. And a very interesting point that's been emerging both from theory and from some recent observations is that it appears that the quasar needs to be luminous enough for a long time to be able to push gas out of the potential low of the host galaxy. And this is some interesting work by Sylvain Villot on molecular outflows, which indicates that there's this threshold luminosity of a few times 10 to 45 erg per second. So we're really talking about quasar feedback rather than AGN feedback. It needs to be a very luminous object to be able to impact the entire galaxy. All right, let me quickly march through a few ways in which we can observe quasar feedback. This is one of the more popular ways now, observations of extended ionized gas. A few years ago, we set out to do this with Gemini Integral Field Unit instrument, and we have been predominantly using type 2 quasars, focusing on radial quiet objects, so those that are not driven by jets. So the quasar is in the center and is illuminating extended gas, and if this gas is moving due to quasar-driven winds, then we should be able to see this in spatially resolved line observations. This is a typical optical spectrum. This is O3 doublet, O3507 and O34959. Multi-gas in decomposition. I wouldn't put any attach any physical significance to these components, but this is very typical. There is a very broad component of a couple of thousand kilometers a second, perhaps, and the lines show blue shifted asymmetries. And in spatially resolved observations, the key observables that we find in these objects are that they have extended regions of high line of sight velocity dispersions and extended regions of blue shifted asymmetries. And the picture we have in mind for these outflows is if you have a roughly spherically symmetric outflow, then along your line of sight, you're seeing stuff that's moving towards you and stuff that's moving away from you. And so the line of sight velocity dispersion roughly tells you what the physical velocities of the gas are. And the blue shifted asymmetries are a classical signature of the outflow. If you have a little bit of dust embedded in it, then the stuff that's redshifted moving away from you is preferentially extincted by dust, and then you see the enhanced blue shifted side. And in this picture, we derive typical outflow velocities of about 800 kilometers a second. So these are low redshift objects at about redshift 0.5. This is now a very popular technique. This is seen in all IFU surveys. Many groups are working on this, including a lot of the people in the audience. A lot of really interesting results are coming out of this technique. Something that we have found at very high redshifts, which is very important because the high redshifts between redshifts 2 and 3 still then said the peak epoch of galaxy formation, and perhaps a key point in the evolution of massive galaxies, so something where we really are interested in examining the effect of quasar feedback on massive galaxies. We have found a population of red quasars at redshifts between 2 and 3 with very unusual optical properties. This is work done led by Nick Ross. And we have been collecting observed frame near-infrared rest frame optical spectra of these objects. And these are example VLT spectrum. This is O3507, O34959 H beta, where everything is blended together in this unrecognizable mess. So for comparison, this black line is one of those red quasars. The red line is a typical low redshift type 2 quasar with a full width at maximum of 700 kilometers a second. Here, the full width at maximum is 5,000 to 6,000 kilometers a second. So this is a narrow line region of quasars with velocities of 5,000 kilometers a second, implying that the physical velocity of the stuff, radial velocity, if you will, is greater than 3,000 kilometers a second. There are almost no objects like this at low redshift. We have done statistics with various survey data. These are extremely luminous objects, 10 to 47 and above per second. They're probably close to 8-10 accretors, so perhaps this has something to do with that. We are conducting all kinds of follow-up observations on the sample, including spectropolarimetry to probe the geometry of these outflows, and this is on Rachel Alexander's poster right outside. Okay, something completely different. Sunyaev-Zildovich effect from quasar feedback. As the quasar-driven wind propagates through the galaxy and circumgalactic medium, it produces this post-shocked, very hot gas, low density, so that it's not really visible in any sort of emission lines, or even too hot for X-rays probably. So this is this overpressured bubble that's expanding into the intergalactic medium. And this is exactly the kind of stuff where you could be sensitive to it using the Sunyaev-Zildovich effect. The Sunyaev-Zildovich effect is when you have a CMB photon propagating, scattering off some hot gas, and then getting to the observer, and that produces a very subtle spectral distortion of the cosmic microwave background. So we went out and looked for it using Atacama Cosmology Telescope data and Herschel data. This is work led by James Chu student Denham Crichton. This is what the data looked like. We stacked data on 20,000 Sloan quasars. This is in different bins of redshift. And And these are images of quasars of different frequency. These are ARC data. These are Herschel data. Here's our quasar, nice and bright. The SED here is dominated by the dust. And then once you subtract the model for the spectral energy distribution, you look for this very subtle spectral distortion associated with the SD effect. And we detected it. It's a 3 or 4 sigma detection, so I'm not going to oversell it. But it's doing all the right things. For example, it's proportional to quasar luminosity, which is very exciting. And when we model these results, we find that about 15% of the quasar luminosity is being dumped into this bubble, which is a very large number. And so we're doing some follow-up work with numerical simulations to try to see how realistic this is in the simulation of galaxy formation. All right, and Rachel is now going to talk about the recent work on the radio emission and radio quiet quasars.
Thanks so much, Nadia. My name is Rachel Alexandroff. I'm a graduate student at Johns Hopkins. I'm going to talk very briefly about how our work trying to uncover the nature of the radio emission in radio quiet quasars might be able to tell us something interesting about new evidence for quasar feedback. So while the distribution of radio power we see in quasars spans a range of magnitudes, there's still open discussion as to whether this distribution in the radio luminosity is just a smooth function or in fact is bimodal. And the interesting question is, if there is a bimodality in the radio luminosity function of quasars, this might suggest that for radio quiet objects, there is in fact a different mechanism that's producing the radio emission in these objects. So we know that the radio emission in radio loud quasars is coming from these jets that Nadia mentioned, but perhaps this isn't true at lower radio luminosities, implying perhaps that not every supermassive black hole is capable of launching a jet. So if it's not jets that are providing the radio emission in radio quiet quasars, what is it? A lot of groups are suggesting that this could be due to star formation, but in the objects we study that are extremely volumetrically luminous, we find that the predicted radio luminosity due to other star formation measures, such as the far infrared luminosity, is a factor of 10 too low to explain the observed radio luminosity. So, over here. So something else must instead be responsible for the radio emission in our objects. In addition, our group and others are seeing intriguing new evidence that the radio luminosity of quasars is in fact correlated with the Kolmogorov maximum, or the outflow speed as measured by the oxygen 3 emission line, which leads us to one possible explanation, which is that the radio emission that we are seeing in radio quiet quasars is in fact driven by quasar winds, where radio synchrotron emission from shocks is what's producing the radio emission that we see. And several other groups have presented theories to that effect. So we're the first people to suggest this. So we are now left with 2 hypotheses if we can rule out star formation as the source of this emission. Compact jets, which are just a scaled down version of the large jets we see in radio loud quasars, and synchrotron emission from quasar winds as the possible explanations for the radio emission in radio quiet quasars. So the question is now, can we distinguish between these 2 sources of emission? And our group is starting to see hints that a combination of 3 factors, the radio luminosity, the radio morphology, and the spectral index, may be able to provide us a hint as to the origin of this radio emission. So, in a pilot sample of objects that we've looked at, in addition to a couple of other objects where you were able to resolve the emission from radio quiet quasars, which we think is starting to occur on galaxy scales, so scales of a couple kiloparsecs. We were able to then get either, as is the example here with the teacup age again, resolve spectral indices across the entire galaxy, or in our case, spectral indices for the core and the lobes separately. And we see a number of structures similar to this where we're resolving both a radio core and radio lobes. But we see not only a steep spectral index in the radio lobes, as you would expect for a jet, but also a steep spectral index in the radio core, which is different than you would expect for a very compact jet, where you would expect to see a flat spectrum in the unresolved radio core. So this leads us to one of two conclusions. Either one, we are seeing compact hotspots from the jet in the unresolved radial core, and that, coupled with the radial lobes, implies a duty cycle for the jet of about 10 to the 7 years, which is a number that comes up in other lines of evidence for the timing of these kinds of mechanisms. Or potentially, we are seeing evidence for synchrotron emission from quasar winds as the driving force behind the radio emission in radio quiet quasars. The other interesting result that you can hear more about if you stop by my poster, which is number 14, is that we are seeing the first hints of the extension of this relationship we talked about between the radio luminosity and the outflow speed at high redshift. So this is data from redshift around 2.5, where we've stacked a number of quasars, both with VLA data that we ourselves collected and with and from a sample of 85 quasars in FIRST, and we find, at least in these stacks, that there appears to be a correlation between the full width half maximum of the oxygen 3 line and the radioluminosity. And neither of these samples were selected on either of those properties, either the radioluminosity or the full width half maximum of their oxygen 3. So to wrap it all up, our group and others are seeing growing observational evidence for powerful galaxy-wide quasar waves, and we're seeing this across a variety of wavelengths, so in different phases of the gas, both in ionized gas, molecular gas, also in bubbles, and we're seeing evidence for the volume filling component. And we're seeing this evidence in radio quiet objects, so any feedback mechanisms in these objects are not being powered by powerful radio jets. And as a result, we are proposing that the radio emission in these radio quiet quasars is a byproduct of shocked winds. For more, stay tuned for a talk this afternoon by a postdoc in our group, Dominica de la Salle, on the effect of quasar feedback on star formation. Thanks.
Questions?
Hi, I had a question about the AZ effect. So there's another paper by Ruan et al. And the numbers seems to be different. Do you have insights as to? I mean,
Yes.
I know they're quite uncertain. So.
Yes, so there are two more papers. There's a paper by Ruan, which preceded ours by a few months, and then there's a paper by Verdier by the Blank Collaboration, where we are within a week or two of each other. And the Verdier paper finds as the effect using a different sample of quasars, blank is all sky, so this is a different sample of quasars, which is within several tens of % power, so it's very close, so it's extremely encouraging. We think, so for the Ruan paper, and again, I'm not the one who was analyzing the SZ, the CMB data for this project, but I can sum up what Toby Nerich has explained to me, which is that the Ruan paper was based on the maps of the Y parameter produced by the Spergel group. And it appears that in the production of this Y parameter map, the relevant, the way we do this is we need to subtract in annuli the background for our SCD measurement. And so this is not, you cannot use the Y parameter maps computed without this in mind for a pointed observation like this. And they have dug deep into this, and I think this is where they found the problem. So it appears that this is not a correct measurement, period. So it is way too powerful. It's about 2 orders of magnitude more luminous. So we would have unambiguously seen it. I mean, it's 100 times more than what we're seeing in these data and what the Planck people are seeing in their data.
I have a short question about constraints on geometry of the outflows. Do you have constraints on geometry, or to which redshift you can constrain the geometry?
Okay, so our best spatially resolved observations are coming are at the low redshift end, 0.5 or so. So this was actually one of the bigger surprises of our data, that the outflows seem to be these blobby, amorphous things. There is some directionality to it. Dominica might or might not talk about this. The quasar does illuminate this outflow, and therefore if the illumination pattern is directed slightly towards you, then you should be able to see that this side is approaching and this side is receding, and this is exactly what we see. But nonetheless, the outflows seem pretty round, and this is a little bit surprising to me still. I suspect there is a little bit of contribution, or more than a little bit of contribution, from shock ionization. So where the quasar is illuminating, this is the dominant source of ionization, but where the quasar is not illuminating, the gas is also outflowing, but shocks may be the dominant source of ionization. And we see this using some shock diagnostics in the stacked spectrum. The most interesting evidence for directionality is in these bubbles. I had to skip that for the main talk, but we do have some candidate bubbles, the ones that break out of the denser regions of the galaxy. So for example, in this case, high dispersion area here in the galaxy, and then as these bubbles propagate, they plow shells, which show much lower velocity dispersions, and this is the blue stuff seen over here and over here, and those are the same shells that Rachel and Chris Harrison and various other people are seeing in the radio data, coincident with the O3 emission. So we see evidence for bubbles as well.
Thank you. Okay, let's thank our two speakers.